Tantor Audio, a division of Recorded Books, presents The Earth, a very short introduction, by Martin Redfern, narrated by Diane Cardea.
Chapter 1. Dynamic Planet. Once a photograph of the Earth, taken from the outside, is available, a new idea as powerful as any in history will be let loose. Sir Fred Hoyle, 1948. How can you put a big round planet in a small flat book? It is not an easy fit, but there could be two broadly different ways of attempting it. One is the bottom-up approach of geology, essentially looking at the rocks. For centuries, geologists have scurried around on the surface of our planet with their little hammers, examining the different rock types and the mineral grains which make them up. With eye and microscope, electron probe, and mass spectrometer, they have reduced the planet's crust to its component parts. Then they have mapped out how the different rock types relate to one another, and through theory, observation, and experiment, they have worked out how they might have got there. It has been a huge undertaking, and one that has brought deep insights. Collectively, the efforts of all those geologists have built a giant edifice on which future Earth scientists can stand. It's as a result of this bottom-up approach that I can write this book. But it is not the approach I will use. This is not a guide to rocks and minerals and geological map-making. It is a portrait of a planet. The new view on our old planet is the top-down approach of what has come to be known as Earth system science. It looks at the Earth as a whole and not just frozen in time in the moment we call now. Taken over the deep time of geology, we begin to see our planet as a dynamic system, a series of processes and cycles. We can begin to understand what makes it tick. The view from above. The prediction above was made by astronomer Sir Fred Hoyle in 1948, a decade before the dawn of spaceflight. When unmanned rockets took the first pictures of the Earth from outside, and when the first generation of astronauts saw for themselves our world in its entirety, the prediction came true. It's not that those first views told us much we didn't already know about the Earth, but they gave us an icon. And to many of the astronauts who witnessed the view firsthand, it gave an emotional experience of the beauty and seeming fragility of our world that has lived with them ever since. It is perhaps no coincidence that Earth sciences were undergoing their own revolution at the same time. The concept of plate tectonics was at last gaining acceptance 50 years after Alfred Wegener originally suggested it. Exploration of the ocean floor revealed that it was spreading out from a system of mid-ocean ridges. It had to be going somewhere, forcing continents apart or into one another. The unimaginable masses of continent-sized plates of rock were on the move in an elaborate and ancient waltz. It was around the same time, and with the same icon of that small blue jewel we call Earth floating in the blackness of space, that a global environmental movement began to form, a mixture of those with a sentimental attachment to endangered species and rainforests, and scientists taking on board a new view of complex, interacting ecological systems. Today, most university departments and research groups use the term Earth Sciences rather than geology, recognizing a broadening of the discipline beyond the study of rocks. The term Earth Systems is becoming widespread, recognizing the interrelated dynamic nature of processes that include not only the solid, rocky Earth, but its oceans, the fragile veil of its atmosphere, and the thin film of life on its surface as well. It is as if our world were an onion, a series of concentric spheres, from magnetosphere and atmosphere, through biosphere and hydrosphere, to the layers of the solid Earth. Not all are spherical, and some are much less substantial than others, but each manages to persist in a delicate equilibrium. Each component of such a system is seen not as something fixed and unchanging, but more like a fountain, maintaining its overall structure perhaps, but constantly changing as material and energy pass through it. If rocks could talk. Rocks and stones are not the most forthcoming of storytellers. They have a tendency to sit there gathering moss, only rolling when pushed. But geologists have ways of making them talk. They can hit them and slice them, squeeze them, squash them, strain and stress them until they crack, sometimes quite literally. If you know how to look at them, rocks can tell you their history. There is the recent history of the rock on the surface, how it has been weathered and eroded, the telltale scars of wind, water, and ice. There can be deeper scars that record periods of heat and pressure and deformation when the rock was buried. Where these changes are extreme, the rocks are known as metamorphic. Then there are clues to the origin of the rocks. Some show signs of having once been molten and pushed up from deep within the earth to erupt out of volcanoes, or to intrude into pre-existing rocks. These are the igneous rocks. The size of mineral grains within them can reveal how quickly they were cooled. A large mass of granite cools slowly so that crystals in it are large. Volcanic basalt solidifies rapidly, and so is fine-grained. Rocks can be made of the ground-down remains of previous rocks. Here, the size of the fragments tends to reflect the energy of the environment that laid them down, from fine shale and mudstone deposited in still water, through sandstones to coarse conglomerates washed down by raging torrents. Others, such as chalk and limestone, are chemical deposits accumulated as living systems took carbon dioxide from the atmosphere and precipitated it in seawater, turning, as it were, the sky into stone. Even individual mineral grains have their story to tell. Mineralogists can strip them apart atom by atom in mass spectrometers so sensitive that they can reveal different ratios of isotopes, different atomic forms of the same elements, even among trace constituents. Sometimes these can help date the grains so that we know if they came out of still more ancient rock. They can also reveal the stages of growth of a crystal, for example of diamond, as it passes through the Earth's mantle. In the case of isotopes of carbon and oxygen in minerals derived from marine organisms, it's even possible to estimate the temperature of the sea and the global climate when they formed. Other worlds. The trouble with the Earth is that it is the only one we've got. We can only see it as it is today, and we can't tell if it is here simply due to some happy accident. That's why Earth scientists are taking a renewed interest in astronomy. Powerful new telescopes sensitive to infrared and sub-millimeter wavelength radiation can stare deep into star-forming regions to see what may have happened when our own solar system was born. Around some of the young stars, they have revealed dusty halos, known as protoplanetary disks, perhaps new solar systems in formation. But the search for fully formed Earth-like planets is more difficult. To see directly such a planet in orbit around a distant star would be like trying to spot a small moth close to a powerful searchlight. But indirect methods have led to the discovery of planets in recent years, mainly by detecting tiny wobbles in the motions of the parent stars due to gravitational effects. The clearest effects, and therefore the first discovered, seem to be due to planets far bigger than Jupiter orbiting far closer to their stars than the Earth is to the Sun. So they could hardly be termed Earth-like. But evidence is beginning to accumulate for solar systems more like our own, with multiple planets. Though small and hospitable planets like Earth will be hard to detect. To see such planets directly would take telescopes in space that we can scarcely dream of. There are ambitious plans underway in both the USA and Europe for a network of linked infrared telescopes. Each would have to be far bigger than the Hubble Space Telescope, and 4 or 5 of them would have to fly in close formation to combine their signals to resolve the planet. They would have to be as far out as Jupiter to get beyond the dusty infrared glow of our own planetary system. But then, they might be able to detect vital signs in distant planetary atmospheres, and, in particular, they might detect ozone. That would imply Earth-like conditions of climate and chemistry, plus the existence of free oxygen, something which, as far as we know, can only be maintained by life. Signs of life. In February 1990, on its way out of the solar system after encounters with Jupiter and Saturn, the Voyager 1 probe beamed back the first image of our entire solar system as it might appear to visitors from another star. The picture is dominated by a single bright star, our Sun, seen from 6 billion kilometers away, 40 times the distance from which we are used to seeing it. The planets are scarcely visible. The Earth itself is smaller than one picture element in Voyager's camera, its faint light caught in what looks like a sunbeam. This is our whole world, seemingly just a speck of dust. But to any alien visitor with the right instruments, that tiny blue world would immediately attract attention. Unlike the giant stormy gas bags of the outer planets, cold, dry Mars, or the acid steam bath of Venus, the Earth has everything just right. Water exists in all 3 phases: liquid, ice, and steam. The atmospheric composition is not that of a dead world that has reached equilibrium, but one that is active and must be constantly renewed. There is oxygen, ozone, and traces of hydrocarbons, things that would not exist together for long if they were not constantly renewed by living processes. This alone would attract the attention of our alien visitors, even if they could not detect the constant babble of our communications, radio, and television. Magnetic bubble. Geophysics goes way above our heads. I don't mean by that it is incomprehensible, but that the physical influence of our planet extends far above its solid surface, way out into what we regard as empty space. But it is not empty. We live in a series of bubbles, nested like Russian dolls, one within another. The Earth's sphere of influence lies within the greater bubble dominated by our Sun. That in turn lies within overlapping bubbles blown by the expanding debris of exploding stars or supernova long, long ago. They are all within our Milky Way galaxy, which is in turn a member of a supercluster of galaxies within the known universe, which itself may be a bubble in a quantum foam of worlds. The Earth's atmosphere and magnetic field shield us, for the most part, from the radiation hazards from space. Without this protection, life on the Earth's surface would be threatened by solar ultraviolet and X-rays, as well as cosmic rays, high-energy particles from violent events throughout the galaxy. There is also a permanent gale of particles, mostly hydrogen nuclei or protons, blowing outwards from the Sun. This solar wind speeds past the Earth at typical velocities of around 400 kilometers per second and goes 3 times faster during a solar storm. It extends for billions of kilometers out into space, beyond all the planets, and maybe beyond the orbits of comets, which reach out many thousands of times further from the Sun than does the Earth. The solar wind is very tenuous, but it is sufficient to blow out the tails of comets as they come closer into the heart of the solar system, so the tails always point away from the Sun. It also features in imaginative proposals for propelling spacecraft with vast gossamer-thin solar sails. The Earth is sheltered from the solar wind by its magnetic field, the magnetosphere. Because the solar wind is electrically charged, it represents an electrical current, which cannot cross magnetic field lines. Instead, it compresses the Earth's magnetosphere on the sunward side, like the bow wave of a ship at sea, and stretches it out into a long tail downwind, which reaches almost as far as the orbit of the Moon. Charged particles caught within the magnetosphere build up in belts between the field lines where they are forced to spiral, generating radiation. These radiation belts were first spotted in 1958 when James Van Allen flew the first Geiger counter in space on board the American Explorer 1 satellite. They are areas to be avoided by spacecraft hoping for a long life and would be lethal to unprotected astronauts. Where the Earth's magnetic field lines dive down towards the poles, solar wind particles can enter the atmosphere, sending atoms ricocheting downwards to produce spectacular auroral displays. At the top of the atmosphere, the hydrogen ions of the solar wind itself produce a pink haze. Lower down, oxygen ions produce a ruby-red glow, while nitrogen ions in the stratosphere cause violet blue and red auroras. Occasionally, magnetic field lines in the solar wind are forced close to those of the Earth, causing them to reconnect, often with spectacular releases of energy which extend the auroral displays. The fragile veil. There's no clearly defined height that marks the top of the atmosphere. 260 kilometers above the ground, in low Earth orbit where the space shuttle flies. You're above almost all the air, and the pressure is 1 billion times less than it is on the ground. But there are still about 1 billion atoms in a cubic centimeter up there, and they are hot and electrically charged, and hence can have a corrosive effect on space vehicles. At times of maximum solar activity, the atmosphere expands slightly, exerting more frictional drag on low spacecraft, which have to be boosted up to stay in orbit. The upper atmosphere, above 80 kilometers, is sometimes known as the thermosphere, because it is so hot, even though it is so rarefied that you would not burn your skin on it. This region of the atmosphere also absorbs dangerous X-rays and some of the ultraviolet radiation from the sun. As a result, many atoms become ionized, that is, they lose an electron. For this reason, the thermosphere is also called the ionosphere. Because the ionosphere is electrically conducting, it will reflect certain frequencies of radio waves, making it possible for short-wave radio transmissions to be heard around the world, well over the horizon from the transmitter. Even a mere 20 kilometers up, below the thermosphere, the mesosphere, and most of the stratosphere, we are still above 90% of the air in the atmosphere. It is at around this height that we encounter the tenuous ozone layer, molecules containing 3 oxygen atoms. Ozone forms when ordinary oxygen molecules of 2 atoms are split by solar radiation, and some recombine in 3s. Ozone is a highly effective sunscreen for the planet. If all the ozone in the Earth's atmosphere were concentrated at ground level, it would form a layer only about 3 millimeters thick. But it still filters out virtually all of the most dangerous shortwave UVC radiation from the sun, and most of the medium wavelength UVB rays as well. Thus, it protects life from sunburn and skin cancer. The ozone layer has been severely depleted by chemicals such as CFCs, chlorofluorocarbons, released by human activity, leading to a generalized thinning of the layer and more specific holes over polar regions in the still cold air of spring. International agreements have slowed the release of CFCs, and the ozone layer should recover, but the chemicals are long-lived, and it will be some time yet before it does. Circles and cycles. It is in the lowest 15 kilometers of the atmosphere, the troposphere, that most of the action takes place. This is where weather happens. It's where clouds form and disperse, and where winds blow, transferring heat and moisture around the planet. In a dynamic planet, everything seems to go round in circles, flows of energy. And here, close to the surface, these cycles are driven by solar power. There are the obvious cycles of day and night as the Earth spins on its axis and the ground alternately heats and cools, and the annual cycle of the seasons as the Earth orbits the Sun, presenting first more of one hemisphere then more of the other to the sunshine. But there are longer cycles too, such as the wobble of the Earth's axis over tens of thousands of years. Just as the Earth orbits the Sun, so the Moon orbits the Earth. It takes about 28 days to complete an orbit, giving us our months. As the Earth spins on its axis, the Moon's gravity pulls a bulge in the oceans around the planet, creating tides. This also acts as a brake on the rotation of the Earth, slowing down the days. Daily growth bands in fossil corals 400 million years old suggest that their days were several hours shorter than our own. The Moon helps to stabilize the orbit of the Earth, and hence the climate. But there are far longer cycles at work too. The Earth's orbit around the Sun is not a perfect circle, but an ellipse, with the Sun at one focus. Hence, the distance of the Earth from the Sun varies during its orbit. In addition, the degree of variation itself changes over a 95,800-year period. Also, the Earth's rotation axis slowly wobbles or precesses like a spinning top off balance. Over a period of 21,700 years, the planet's axis traces out a complete cone. At present, the Earth is nearest to the Sun during the northern hemisphere winter. The inclination of the Earth's spin axis with that of its orbit around the Sun, the obliquity, also changes on a 41,000-year period. These so-called Milankovitch cycles add up over tens or hundreds of thousands of years to affect climate. They have been blamed for such phenomena as the ice ages that have affected the Earth over the last 3.25 million years. But the reality is probably even more complex, with their effects amplified or reduced by factors such as ocean circulation, cloud cover, atmospheric composition, volcanic aerosols, the weathering of rocks, biological productivity, and so on. Solar cycles. Cycles of change are not restricted to the Earth. The Sun can change too. Over its 5 billion-year history, the Sun has been getting progressively warmer. Surface temperatures on Earth have remained more constant, however, as levels of greenhouse gases have fallen over the same time. This was largely due to the effects of life, as plants and algae consumed carbon dioxide that acted like a blanket to keep the young Earth warm. There have been other solar variations as well. There is a regular solar cycle of 11 years, which sees a rise and fall in sunspot activity, in turn reflecting the cycle of solar magnetic activity which produces storms and the solar wind. Other sun-like stars seem to spend about a third of their time free of sunspots, a state called a Maunder minimum. That happened to our Sun between 1645 and 1715 AD. Solar power only dropped by about 0.5%, but this was enough to plunge northern Europe into what has become known as the Little Ice Age, with a series of particularly severe winters. The River Thames in London froze over, and markets and frost fairs were held on it. Hot air. The Sun distributes its warmth unevenly, warming up equatorial regions the most. As the air warms, it tries to expand, increasing atmospheric pressure. To try to restore equilibrium, winds begin to blow, and the air circulates. Whilst all this goes on, the Earth continues to rotate, giving the air angular momentum. That is greatest at the equator and results in the so-called Coriolis effect. The atmosphere is not firmly coupled to the solid planet, so as winds blow away from the equator, they have a momentum that is independent of the rotating surface beneath. This means that, relative to the surface, the winds curve to the right in the northern hemisphere and left in the south. This leads to rotating systems of high and low air pressure, the weather systems that bring us rain or sunshine. Land masses and mountain ranges influence the circulation of heat and moisture too. Until the Himalayan mountain range began to rise, there was no Indian monsoon, for example. And most importantly, the oceans play a huge part in storing heat and transporting it around the globe. The top 2 meters of the ocean have the same heat capacity as the entire atmosphere. At the same time, heat circulates in ocean currents. But currents on the surface are only half the picture. A good example is the Gulf Stream in the North Atlantic. That carries warm water north and east from the Gulf of Mexico, and is one of the reasons why the climate of Northwest Europe is much milder in winter than that of Northeast America. As the warm water heads north, some evaporates into the clouds, which always seem to fall on British holidaymakers. The remaining surface waters in the ocean cool and become progressively more salty. As a result, they also become denser and eventually sink down to flow back south in the deep Atlantic, completing the conveyor belt of the ocean circulation. Sudden freeze. About 11,000 years ago, the Earth was emerging from the last ice age. Ice was melting, sea levels were rising, and the climate was getting generally warmer. Then suddenly, in the space of a few years, it turned cold again. The change was particularly marked in Ireland, where pollen in sediment cores shows that the vegetation suddenly reverted from temperate woodland back to tundra, dominated by a little plant called the dryas. Wally Broker of the Lamont Doherty Geological Observatory has worked out what may have happened. As the ice sheet over North America receded, a vast lake of fresh meltwater, far bigger than the present Great Lakes, built up in central Canada. At first it drained over a great ridge of rock into the Mississippi. As the ice receded, it suddenly opened a far lower passage down the St. Lawrence River to the east. The vast lake of cold, fresh water drained into the North Atlantic almost instantaneously. So much water was involved that it caused an immediate sea level rise of 30 meters. It diluted the salty surface water of the North Atlantic and put a virtual stop to the conveyor belt of ocean circulation. Thus, there was no warming current into the North Atlantic, and Arctic conditions returned. 1,000 years later, the ocean circulation resumed as quickly as it had vanished, and a temperate climate returned. The North Atlantic deep water, together with cold bottom water from the Antarctic, finds its way at depth as far as the Indian and Pacific Oceans. The deep current continues into the North Pacific, slowly accumulating nutrients as it goes, before it rises again to the surface. Global greenhouse. Some of the gases in the Earth's atmosphere act rather like the glass of a greenhouse, letting sunlight in to warm the ground, but then preventing the resulting infrared heat radiation from escaping. Were it not for the greenhouse effect, average global temperatures would be around 15 degrees Celsius lower than they are, making life almost impossible. The principal greenhouse gas is carbon dioxide, but others, including methane, play an important role. So does water vapor, an effect that is sometimes forgotten. Over hundreds of millions of years, an approximate balance has been struck with plants removing carbon dioxide from the atmosphere through photosynthesis, and animals returning it by respiration. Vast quantities of carbon have been buried in sediments such as limestone, chalk, and coal. Volcanic eruptions have released carbon from inside the Earth. In recent years, concern has grown over what should be termed the enhanced greenhouse effect, the very significant rise in greenhouse gas levels in the atmosphere resulting from human activity. The burning of fossil fuels such as coal and oil are prime culprits, but so are agricultural practices which produce methane, and deforestation which releases carbon dioxide from timber and soils, as well as reducing the plant cover to absorb it again. Climate models suggest that these activities could result in a global temperature rise of several degrees over the next century, accompanied by greater extremes in weather and a possible sea level rise. Climate change. The steady annual rise in carbon dioxide levels has been carefully recorded from an isolated mountain peak in Hawaii since 1958. More than 130 years of meticulous weather readings around the world confirm an average global warming of about half a degree, with the effect particularly.
Sample complete. Ready to continue?